All right, we're going to talk about the infinite geometric series, which is in the form S equals the sum from, and there's starting with 1 and they're starting with 0. So for pre-calculus, we usually start with 1. When we get into BC calculus, we usually start with 0. But here we go. I equals 1 to infinity of a r to the I minus 1. Now, if the absolute value of r is less than 1, then this is going to end up equaling a over 1 minus r. So that is your infinite series. And I'm going to prove that. But before I prove that, we're going to look at the finite one, which is s equals the sum from I equal 1 to n, some finite natural number, of a r to the I minus 1. And regardless of what r equals, it's going to end up being a times 1 minus r to the n over 1 minus r. Now, if it's finite, it's going to give you this guy, and it's infinite, it's going to give you this guy. So let's deal with this guy first. I'm going to prove that this equals this, and then we're going to use an infinite count to show that it will end up getting that if it's infinite. So here we go. We're going to let s equal the sum from I equal 1 to n of a r to the I minus 1, which will be a times r to the 1 minus 1, which is r to the 0, which is 1. So a times 1 is a, plus when I is a 2, it'll be a r to the 2 minus 1, which is a r to the 1, which is a r. Then a r squared, then a r cubed, and we're going to go all the way till we get to n, which will give us a r to the n minus 1. Okay, so that looks plain and simple. And how many terms are there? 1, 2, 3, 4, blah, blah, blah. N terms, because here's where n is a 1 and here's where n is a 0. So n minus 1. Yeah, I guess that's going to be n minus 1. No, because that's where it's a 1. Ouch. Yeah, n minus 1 term. Sorry. Okay, let's look at s r. I'm going to multiply that by r. So it's going to be this times r, which is a times r, plus a times rr, plus a rrr, all the way to a r to the n minus 1 plus 1. And notice it also has n terms, 1, 2, 3, 4, all the way to n. So this has n terms and this has n terms. Okay, let's subtract them. Why? Because we can. So if I subtract that side, then I got to subtract this side, which would be all of these guys, a plus ar plus ar squared plus blah, 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 yada, 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 plus ar to the n minus 1. Then I'm going to go minus ar, then minus ar squared, then minus ar cubed, minus dot, 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 minus, right there, the one I did not write, is ar to the n minus 1, and then minus ar to the n. So if I'd go that minus that, I get that minus that. No big deal. Good square algebra. But let's see what really just happened here. S times s minus r, I can factor out the s, and I get 1 minus r. Over here I get an a. I get ar minus ar, which is nothing. Ar squared minus ar squared, which is nothing. Nothing, 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 nothing. Here I got ar to the n minus 1 minus ar to the n minus 1, which is nothing. Then 0 minus ar is minus ar. Now I could factor the a out of that. I get a times 1 minus r. So this equals that. And now to find out what s is, I will divide both sides by 1 minus r. So I get a you check this out, guys. There's an N right there, you bozo, and there's an N right there, dummy. So now, when I divide both sides by 1 minus r, s times 1 minus r divided by 1 minus r is just s, and a times 1 minus r to the n divided by 1 minus r is that. So check it out. S, which is that sum, equals this guy right there. So that worked out pretty good. Now, that's the finite. Let's look at the infinite. If I have S equals the sum from I equal 1 to infinity of a r to the I minus 1, well, let's plug this in. I'm going to get a times 1 minus r. Now, there is no number infinity, but I'm going to write infinity there because we haven't talked about limits yet in this class. But we're going to let that be to a power that never gets a biggest number over 1 minus r. Now, if r is small, as in between -1 and 1, then let's imagine a fraction like 2/3. Well, 2/3 to an infinite power would be 2/3 times 2/3 times 2/3 forever and ever and ever. So it gets smaller and smaller and smaller. I'm going to draw a little graph of that. Here's 2/3 to the 0. Here's 2/3 to the 1. Here's 2/3 to the 2, 3, 4, 5, 6, 7, 8. See how it's heading to 0. So as I go to the right forever, it will get closer to 0 forever. And so this will become a 0, which will be a times 1 over 1 minus r, because that's 1 minus 0. And this, of course, is just a over 1 minus r, which is the thing we were showing it was going to be. Boom. Right there. Now, that's if r is between -1 and 1. Now, r equals 1, it don't equal a thing. If r equals -1, then you get, okay. If it was -1, you're going to be raising -1 to an infinite power, and honestly, that doesn't make any sense. So equals nothing. Now, if r is bigger than 1, like if r is 2, then I'm going to have 2, 4, 8, 16, 32, 64. This guy increases without bound. And so it's going to be divergent. It won't equal anything. And then if I've got, say, equals something that's smaller than -1, like -2, then it's going to be -2, +4, -8, +16, -32. It alternates in also. That is in calculus. You find out we're going to call that divergent. So it only works if r is between -1 and 1, and not including -1 and not including 1. So this is our infinite series if and only if r is between -1 and 1. Boom. So this is the infinite one here, and this is the finite one here. And we'll do both of these in pre-calculus, but this will be the dude that gets used in calculus, will be the infinite series. But you got to know them both. Alrighty, thank you.